Good morning, friends. This is the vision and mission of our institute. The vision statement of our institute is fostering the technical excellence through ethics, sustainable education, innovation, and the research. To achieve this vision, we have the four mission statements. Likewise, we have the vision and mission of our computer engineering department also. The vision statement of our department is to provide high quality computer education, engineering education with socio-moral values. And to achieve this vision, the department have the three mission statements. Likewise, we have the three program education objectives statements of the department. Let's start with the chapter number 3, data link layer. Data link layer is the second layer in the ISO OSI model. Already we have studied this in the last lecture. The first topic in this unit is the error detection. The data can be corrupted during the transmission, and to ensure the reliable communication, the error must be detected and corrected. Basically, two types of the errors are there: single bit error, multi-bit error. Single bit error, only the error happens at the only one bit position. Multi-bit error, two or more bits in the data units are changed. And the third other category of the error is the burst error. Here, the two or more consecutive bits in the data units are changed. To detect the errors, a common technique is used, and that is to introduce the redundancy bit that provides the additional information. That introduction of the redundant bit is nothing but the parity bits. The various techniques for the error detection include the simple parity check, two-dimensional parity check, checksum, and the last one is the cyclic redundancy check, CRC. In the first method of the simple parity check, simply the parity is checked here. So parity is the additional bits added to the original data. Basically, we have the two types of the parity. One is the even parity, second one is the odd parity. Even parity means if the original data contains the even number of the ones, at that time we can say that it's a even parity. On the other hand, if the original data contains the odd number of the ones, we can say that the odd parity. So here in the first method, here only the parity base is checked at the receiver side. So sender while sending the original data adds the parity bit. That parity bit indicating the how many number of the ones are there in the original data, and the sender sends the original data along with the parity bit to the receiver via the one of the transmission medium. Then at the receiver also checks the parity bit, and if the parity bit is matched according to the original data, then the data get accepted by the receiver. If there is something mismatch here, then the receiver simply rejects that data. So one of the drawback of this simple parity check method is that this method is suitable for detecting only the single bit error. On the other hand, this is not suitable for detecting the multi-bit errors. To overcome all these drawbacks, we use the second method, that is a two-dimensional parity check. In this method, the row-wise as well as the column-wise parity bits are calculated, as shown here in the figure. And then the original data along with the final column parities sent to the receiver here. The third method of the error detection is the checksum. So here the original data is divided into the number of the segments here. So as shown in the figure here, this is the original data here divided into the 4 number of the segments here. So K here indicating the number of the segments, and the M indicating the total length of that segments. So ensure that the length of all the segment must be equal. So here onto the sender side, the sum operation is performed. Logical sum operation is performed, or we can say that the logical XOR operation is performed here. In the logical XOR, the output is 1 whenever both the inputs are different. On the other hand, the output is 0 whenever both the inputs are same. So here this sum operation is performed onto the sender side, and then at the last we obtain what is the sum here, and we just need to invert here, and we obtain the checksum here. So then the same process is repeated onto the receiver sides also. At the last again here we obtain the sum here, and then whatever the checksum obtained onto the sender side, we just perform the XOR operation of that checksum onto the sender side with the sum obtained at the receiver side, and at the last the sum obtained is equal to all the ones, and we need to take the complement of that sum. And if we obtain the zeros, it means that the data get accepted by the receiver here. This is the fourth method of the error detection, that is the CRC, stands for the cyclic redundancy check. Here the M indicating the original data, N indicating the number of the bits, number of the zeros to be appended at the original data. So here the division operation is performed, and then as we know that after performing the division operation, the remainder is generated, and this remainder is nothing but your the cyclic redundancy checksum, and at the last of the center side, this CRC is appended to the original data, and then it is sent to the receiver, and the same operation is happening onto the receiver side also. Only the difference is that onto the sender side, the some number of the zeros are appended to the original data, and onto the receiver side, instead of the zeros, the CRC is appended to the original data. So the criteria for appending the number of the zero, that is equal to the number of the bits in the divisor minus 1. For example, if the divisor has the 5 bits, then the 5 minus 1, that is 4, we need to append here the 4 number of the zeros here. Suppose that our original data is 11100 and the divisor is 1001. So the number of the bits in the divisor, these are the 4. So this 4 minus 1 is equal to 3. So here we append the 3 zeros here to the original data, that is the 11100, and here this last 30, nothing but the bits number of the zeros appended here. Then we simply perform the binary division operation here in this way, and at the last we obtain the quotient and remainder. So forget about the quotient, we just focus onto the remainder only. And this, whatever the remainder obtained at the last of the division operation, this remainder we may call as the CRC remainder. So this is the process happening onto the sender side. Onto the receiver side, the original data is appended by the CRC remainder here. So this is nothing but about the CRC remainder obtained onto the sender side. So divisor remains same. Again, we perform the same division operation here, binary division operation here, and at the last we obtain the quotient and as well as the remainder. Forget about the quotient here and just focus on the remainder here. If at the last we obtain the remainder is equal to 0, it means the data is accepted by the receiver. Otherwise, the receiver simply rejects that data. This is one of the example based on that CRC method of the error detection, where the bit string is given to us, and this is transmitted using the standard CRC method, and the generator polynomial is x to the power 4 plus x plus 1. What is the actual bit string transmitted here? So with the help of the given generator polynomial, we just obtain the here the divisor here. So this is the way to obtain the divisor here. So number of the bits in the divisor, these are what here the 5. So how many number of the bits we need to append here to the original data? So that 5 minus 1, that is equal to 4. So here we appended the 4 bits here. We perform the say division of binary division operation onto the sender side. So this is the final remainder obtained here, 110, that we may call as the CRC remainder. So here we appended the CRC remainder here to the original data and perform the same operation. If the remainder obtained finally is equal to 0, it means that the data get accepted by the receiver. Otherwise, the receiver simply rejects that data. Thank you.